To do so. My name is Gustafsson, and I will not start to introduce myself because then you're falling asleep, all of you. I'll start with a movie instead. It used to be more eye-catching, right? This movie is done by the European Commission's news agency called Futures. I don't have to introduce the video itself.
Research and innovation in Futures.
Aviation safety, it's a worldwide concern. This is the story of how European researchers want to prevent further catastrophes with the help of textiles tested in explosive ways. At a British research centre for experimental blasts, a unique experiment is underway.
In this test, we want to measure how effective our prototype is in containing the explosion and the fragments it will emit, along with the subsequent expansion of gases.
E anche l'espansione dei gas.
Researchers have developed a textile container designed to prevent the effects of small bombs hidden inside luggage, which are then carried in aeroplane cargo holds.
Here we've got a typical luggage that people take on aeroplanes on the holidays, so lots of clothes and things. Inside here we've got a surrogate IED, typical of the kind of threats that we face on aircraft these days. So the small charge, typical to bring down an aircraft. We're going to close this up in a short while and pop it into the container.
The first explosion barely affects the prototype, developed under a European Union research project called Flybag.
3, 2, 1.
The container has been constructed with a combination of different layers of technical textiles. Each has its own characteristics. Some textiles have been positioned in different places to withstand the penetration of fragments flying out during the explosion. Some other textiles have been designed to be able to expand in a controlled way, so the container can stretch without tearing itself apart. Besides that, we've produced an internal coating with two aims. The first is to contain the gases generated during the explosion. The second is to strengthen the resistance of the whole structure, so that the coating becomes a sort of flexible composite inside the container.
Damaged baggage is taken out, new baggage is put inside. The amount of explosive is increased by 50% in a second test. The bag still holds tight.
Here comes the explosion and inside the luggage, and the luggage raises the whole container up in the air, and then comes the pressure from the explosion and blows the container up. And now you see the luggage falling down again inside the container. And the air pressure that has blown up the container is now leaking out. You can see that there is a small fire starting inside the luggage, and soon you will see the smoke coming out through the zip. But this will just be for a very short while because it's so little oxygen inside the flybag, so the luggage is not burning for long at all.
Firing point to sentries, report.
Eventually, a more powerful explosive charge will provide the ultimate test. But first we head to Sardinia, Italy. Here, in a maintenance hangar at Olbia Airport, a similar container has been installed inside a commercial plane.
trying to fit it into this Airbus 319 to see if it fits the right way so we can load luggage into it.
Scientists have indeed come here to understand the realities of routine baggage handling.
This is a truly applied research project. We really wanted to produce a prototype that could allow airlines to test the effective implementation of the whole system. So we've produced a full-scale prototype and tested how useful it could be to airlines. Which is to say, can it be easily loaded with baggage and can it be easily operated without the need for particular skills?
Facilmente, non richiedesse particolari tecniche di particolare skill da parte degli operatori.
Airline companies will be the main end users of the textile container, and the local carrier has played its role in developing the prototype for a reason.
Air safety is already tight on commercial flights. We helped to develop this container because we wanted to offer travelers a new tool to guarantee their safety.
Un ulteriore elemento di garanzia per il passeggero.
Back to the UK, the ultimate test is ready. The initial explosive charge has been almost doubled. Researchers hide in a nearby bunker. The scientific slow-motion camera is ready.
You ready, Al? Yeah. 3, 2. But the leg is standing. The plane is crashed, but it's the stop now.
The bag still holds.
Obviously, we wouldn't seek to protect against the maximum amount of explosive that you could possibly get into a bag. So that'd be circa 20 kilos, which would certainly be enough to bring down an aircraft and many domestic buildings, in fact. So we have to balance how much explosive we could protect against how much weight we'd be adding to the aircraft. Lockerbie was less than half a kilo, which brought down a 747. And recently, the DHL attempted attacks were a few hundred grams in toner packages. This system would seem to be able to protect against that kind of attack.
Please, and you're please.
The successful testing is a first step, researchers say, to ensuring that bomb-proof textiles could soon really improve aviation safety in our increasingly crowded worldwide skies.
I worked here from 1974 until 1985, when we were building this university. One of these I was employee was came directly from Gustafsson. Then I went into the production industry, started my own business in composites, fiber composites. I will tell you more about fiber composite and next generation of fiber composite later. First I will focus on this with the innovation I'm working with, because I'll introduce some of my work. You have to look about that. That's me. And working at a small production company in Luleå, I can never compete with production companies in the Baltic states or in the Yellow states or in Poland or somewhere. I can only compete by knowledge about the materials and processing of the material that we're using. And to develop this knowledge, I need money. And a small company doesn't have a heavy body himself to finance the company. We have to cooperate with others, with universities or other institutes or other companies that are well on those subjects that we're interested in. Our way to do it is to cooperate within the European framework programs. You know, the Commission got something called framework programs that usually is running, a program is working usually for 5 to 7 years. And we're right now in the 7th program, FP7. I started with this in mid-90s, and that was something called FP5, the 5th framework program. And it was in 1996 I was invited to a proposal to this called HICO product. E-R-D. And that was about making large fiber composite parts. Traditional, when you see a silver trailer like that, it's steel beams underneath to carry it. That one is self-supporting. It's a sandwich structure in the floor. It means that it is fibers, there's a core material, and fibers on top. And they work together that effective that you don't need any steel beams under. And we developed that during a project called HICO together with, I think it was 19 different institute universities around Europe. And you see, there is no beams, just the fittings, the wheels and the legs. Here you have how we produced the big floor section and part of the walls in one shot. It took us 50 minutes to infuse the resin, 500 kilos, instead of working in mouth with welding steel. The same technique we used for a house producer who wanted to bring more quality to those who uses their flats or this was for a hotel. Usually you just have a bathroom with tiles or plastic carpet on. Here we did a photo print within the floor. And it's also self-supporting, it's a sandwich, and it's done in a mold, so all the slopes are perfect. There will not be standing any water outside the shower. It's always perfect. Could you believe that a shower that works? I can tell you that we've done more than 3,000 different of these. Those specific that you see, it is the hotel room number 1 and hotel room number 3 at a golf hotel. There's a number 1 there. And this is picture from T number 1, hole number 1, from T number 3 and hole number 3. So when you come to a room, you recognize yourself and then raise the level, hopefully, of the one who lives there. Bringing in more than 3 dimensions to a room. We developed a special production technique with steel molds and a technique how to pre-produce different parts to get an effective production. And we can also, we have a robot that cuts, so we can put in the floor heating from the beginning, electrical or water, all done in one shot. Coming out from the HICO project. When we had done the HICO project, we were asked by an Italian company to join them in another project called Polytect. Polytect. And Polytect, we tried to develop a system to make houses in earthquake areas safe. And on this picture you see a house that was destroyed in the Aquila earthquake in Italy in 2009. 2008 was the earthquake. And we took that house and rebuilt it and brought it to Pavia, just south of Milan, and built it on a shaking table. Built it up in its original way, and we shaped it, and it went broken. Because we have recorded the complete earthquake as it was in the origin. And then we glued and laminated some special fibers and some special epoxy resin on the walls, rebuilt the house first, of course, put on these fibers, and we shaped again, according to exactly this Aquila earthquake. And now you will see what happened. Hopefully it works. that was the length of an earthquake, and all the amplitudes and powers of an original earthquake that destroyed the complete city, and one of the houses was rebuilt and reinforced with our technique, and it survived. So now there is a technique developed that you can put on old houses to make them safe. But this is just finished less than a year ago. In these walls, we have mounted monitoring equipment. We have developed monitoring equipment that can measure real small amplitudes. And to do that, we have developed new sensors, nano-piezoelectric sensors that we put on thin glass fibers within this, and therefore we can recognize very small amplitudes. And our goal is to predict an earthquake. Let's say that we can get knowledge 1 hour in advance, that much. Then a lot of people can disappear in time out of their houses if they get a warning like 1 hour in advance. And this system, we are now working with the software for it, so it will not act like a car passing by, because it also gives shaking, of course, but those vibrations is not at the same time as an earthquake coming. We have defined it through amplitudes and effects in it. So that's something we're working on right now. From this HyperPro project, which I focused hard on, I tried to do a good job, I was invited to a German institute called Fraunhofer. Fraunhofer is Europe's biggest research institute. There are 26 places in Germany, a turnover more than €1 billion. But they have one part down in Finland who work with composite materials. And they are interested in bio-based composite materials. You know, traditional composite materials, epoxies and polyester, glass fibers, carbon fibers, aramid fibers, or as we say, Kevlar, they are all synthetic and not that good for their environmental. Therefore, they wanted to have a project trying to get other materials into the composites. And I was invited to join them in this work. One thing we studied was resins, because polyester and epoxy is no good. You know, you use a lot of acetone and styrene and things like that. Not good for the work safety and neither good for the environment. We focused a lot on the hemicellulose. I will explain what hemicellulose is in a while. From that we made an alcohol. And that alcohol polymerizes, getting hard. When you reach a temperature of 138 degrees by itself, self-curing. I think many of you have been to the dentist and they put some plastic in your teeth and they have a blue light, ultraviolet light, and it cures the epoxy they use in your teeth. That is polymerizing. A lot of materials polymerize themselves at a certain temperature. We could also get this to polymerize with lower temperatures by using different types of catalysts. I won't go into the chemistry. But those materials has a lot of shrinkage problem. And you see this boat doesn't look that nice. So we produce a couple of boats until we reach one that is working. And the one that is functioning, we produced in 2004, I think. And I still have it by my bridge back home, my house. And not now, so. One of these companies that were interested in using materials coming from bio-based materials is the biggest shipyard in Europe. It's called Meyerwerft in Papenburg, and they produce these cruise liners. And they were very interested in both working with big assembly structures, like we did for the Zero trailer, but also looking for bio-based materials. So we were invited by these into a new project called D-Light. producing light composite parts for the ship industry. And that's been on in the from 2005 to 2009 roughly. And we produce parts to these. And you know, these cruise liners use a lot of fuel. If I can reduce the weight of such one with 1 ton, they save 1 ton of fuel per year. If you change all these balconies, you know, there are a few balconies along here. They have a balcony floor made of 15mm steel covered with 12mm of teak wood. If I change that into a fiber composite laminate of a modern technique, I change from 353 kilo per square meter to 48 kilo per square meter. That means 100 ton, which means 100 ton of fuel reduction per year. When we had that project, they ordered some extra balconies and they bought a lot of extra job. They found this very interesting. And we delivered some balconies for them. Here is one of them, typical prototype. And there we use the same technique as we used for the bathroom's floor. Instead of putting wood on top, we put a print of wood. We also put in their logo. But the idea was to reduce weight and cost for maintenance. It's just delivered and it's on full-scale test. In the same project, the Delight project, we worked together with one of Europe's biggest producer of ro-ro vessels. You know, a ro-ro vessel, roll-on, roll-off vessel. These big ships where you just from the aft load cars that are transported around the world. So we have made a couple of floors for them too. That is full-scale tested. One floor has been transported over with 150,000 cars so far, and no problem with the technical properties, especially no problem with corrosion. You know, composite material doesn't corrode like iron does. But both these samples has one negative thing. We don't fulfill the SOLAS regulations about fire safety. The SOLAS regulations are these regulations held by the classifications companies. You should have heard about DLV, the Norske Veritas, the Germanische Lloyd, the English Lloyd. You know, we call them insurance companies, but they are classifications company who says the rules for a certain boat to get insurance. And those materials doesn't fulfill the fire properties. So they are not allowed to be used commercially yet. Therefore, we work with that, and I will tell you more about that in a moment. From this Polytech project, and some operators out, I was invited to a project called Flyback. And Flyback was the introduction film, which I tried to keep you awake with, right? And I have another short film telling you how we worked when developing this container. And then I have to use this one. I think you don't like the music. To manage to design this one, we started to take the standard aluminium container that you use, like this, and blow it. And we had a lot of cameras when we blew it. High-speed cameras that we could study the explosion. Not just what happened, we could also study the power in it, how it damaged the luggage inside, how it damaged the container, and we started to simulate it. Most of these simulations were done by a company called Chatman in the very south of Italy, down on the heel, as you say. And all the past full-scale tests we did at Plastic Company in Boston, outside Manchester, England. And here is the composite floor and back wall. Tested, everything was simulated first So we had some figures to do the technical design, and it was not enough with the cover. We needed some extra bearings, so we don't want too much extension, so we would crush the wall of the airplane. Here you see it mounted in. So from this we could put the properties we needed on the textiles, on the composite parts, and on the extra panels, and on the fittings, so we wouldn't damage. But what we also had to study, it was how to close it in a way that it would work. And we had, this is the team, we had to develop a zip that could manage the explosion. And you see it's quite heavy zip. But this one has been used on 7 different explosions of more than 500 grams of explosives and still function. And we produced 4 of these for testings. And from this, we have now a patent pending, owned by our 9 partners. So we have 1/9 each, and we're waiting for the results of the patent. But meanwhile, we're already in negotiation with some air equipment companies who want to have a license for the production. I don't know if my company will be the producer of the composite part, or they will be licensed out. Probably be licensed out to be production in a cheap country. Because the knowledge was brought into it when we developed it. To mass produce it, it is just a standard knowledge. We do a technical transfer, and hopefully get paid for that. And while we were preparing these computers, waiting for you, I had an email from the European Commission saying that we will get 5,750,541 euros extra to go further on and develop this technique for other applications than just a container, for other bomb-proof applications. It arrived less than 40 minutes ago. Thank you. That means that we can keep on working for at least 3.5 years. And part of that will be used here in Luleå. This is another thing, a typical coming out from such a project. Bombardier needed handles to the subway in Stockholm, to the underground in Stockholm, and nobody knew how to produce it. The technical design was done, but nobody knew how to find out to produce such a handle. And though they heard about that we have developed technique in other applications, we had the question from Bombardier, can you develop new production technique to do these handles? And we did it, and they ordered 3,240 handles. And most of them are produced by students of the Technical University of Luleå. Why? You see, there used to be every year a team building a car that goes for the Echo Marathon down in Germany, right? And that they, part of that, always build the body, the chassis, in our facilities. And they became quite keen on working with composite materials, and the men working in our factory were quite bored of producing the same part. So a lot of students worked on the evenings and weekends producing handles that winter. And I think they were quite pleased, and so were we. These are the molds that they are produced in. I won't tell you so much about the technique behind it because we can't get IP rights on it, we have only the know-how. And that's what we're doing now. We use both vacuum and rather high pressure. To manage to get orders of this kind, you have to have a company that has quality control systems, ISO certificated, you have to have work safety, and you have to have environmental programs. 1001, 2000 for quality, highest level, of course, and 14001 for environmental. I think some of you have seen these ice hockey helmets. We've done them, developed the technique for it. We don't produce it anymore. They are made in some cheap country. But if you see somebody with a helmet sold in USA or Canada and called Reebok, it's produced in Luleå. But nobody knows. When the Biocom project was ended, I was very enthusiastic of getting rid of styrene, acetone, polyester, epoxy, and other synthetic materials. I wanted to see something bio-based, because I think life is of such high quality, so we shouldn't destroy what we live in. We have enough of synthetic materials. So I contacted a lady in Finland called Johanna Lampinen, and a very clever guy in Genoa, Italy, called Andrea Ferrari, and said, I want to make another project about biomaterial. I want to develop something. So we had a 2-day meeting in Rome in 2007 and wrote a proposal to the European Commission. And we called that proposal WODI. And the Commission accepted it, and we got nearly 10 million euros to work with it. And we've been on for 3 years now. We have last year left. But when we were working with this, I had a telephone call in November 2009 from the Maritime Museum of Stockholm. You know Stockholm, Fjordfest, about 1,000 kilometers out town. And they asked, we are now environmental certificated. We need some nice stands that are double curved, difficult to produce in wood. We need to have them made in composite material, but we don't want to have polyester epoxy. We have heard from the European Commission that you up in Luleå can do this in full bio-based materials. Yeah, we surely can in 10 years. Was my answer. But please. Okay, let us do a try, I said. And they sent us some electronic drawings. This is what we want. They said in just before Christmas 2009. And I said it's not impossible to do in glass fiber polyester or in carbon fiber epoxy. No problem to do it. But have we managed to get any bio-based fibers and bio-based resin to manage this already now? Well, let's do a try. So I put our men to work on the robot to make originals looking exactly as the drawings. We had CAD drawings, this was no problem to do that. And to make negative from that then, as molds. You know how you use a mold, don't you? Yes, good. And meanwhile, I called a friend down in Poland who grows flax fibers. I said, I need 1.5 ton of flax fibers. You know, when you have a suit or something in flax, it's hard twisted yarns, like you weave with, to get good mechanical properties of the cloth. But when I want to make a composite, I don't want hard twisted yarns, because I want to wet the single fibers in the yarn. So I glue the single fibers to each other. So I wanted very soft twisted yarns. So I had to try to do that. And that 1.5 ton was sent to a colleague in Italy, Claudia Canal at Selcom, outside Venice, and asked her to make multi-axial mat. When you have cloth material, it's woven, right? You weave, right? And when you weave, the fiber goes like this. And that is not optimum for the strength. Optimum technical properties you get when you have the fiber along, just straight. To do that, we made mats where we lay flat layers in 2 directions, plus 45 degrees and minus 45 degrees, and then we saw, you can see here, the sewing machine, each 1/5 millimeter all along. So we kept these 2 layers together. And from these 1.5 ton of fibers, we managed to get 1.2 ton of mats. That was like half a year later. So I get them in around midsummer 2010 at Luleå. and was very pleased with these mats. It's the first mats I was done this way. Meanwhile, I developed this resin. I showed you a picture earlier with a boat that we used a furfural resin, hemicellulose-based resin. And as you see, the solvent is H2O, it's water. It's no acetone, it's no styrene. Nice for the workers in the factory, right? So we did some testing and we developed, it took us like 4 months to develop a technique to make a laminate with this resin and the flax fibers. But to manage to make these big stands, we needed a sandwich, a core material. And as core material and bio-based, we use balsa wood. Balsa, you know, from Ecuador. Works well, burns well, but this would be inside the laminate, so it's okay. And we used a vacuum technique. We took this negative mold, put the fibers inside, put the balsa wood, put more fibers. We put on a vacuum bag, an extremely flexible folie. And then we tightened it all around and had an outlet around, spiral hoops, and an inlet in the center, and then we put on a vacuum pump, and it turned this way. The flexible bag went down very hard and between every single fiber, really tight into. And when that was stabilized, we had done a lot of tests, as I told you, on the laminate, because the solvent in the resin was water, and natural fiber contains water, and it would cure at 138 degrees. What happened with water around 100? Yeah, no nice at all, right? It starts to boil. So therefore, we needed to reduce the water content. And it was just so much water left that was needed for the polymerization chemistry. So we tested how much pre-drying we should do, at what temperature and for how long. And it was roughly, not to be perfect saying, because it's also RP, roughly 6 hours at 60 degrees in an oven for pre-drying. And then when we had this stabilized, we turned it up to 138 degrees in 10 minutes and it was done. It worked perfect. And we got parts looking like this. Great? All green. Flax fibers, for those who doesn't know what flax is, we in Sweden say lina. Lin, som växten heter. In German, lino. Italian, lino. Linen in German, I think, lino in Italian. And this is how it looks now in Stockholm, at the museum. I think we made some 25 parts. And that was within the Woody project. I have to look at my paper. I had some white chalk here. Out from the July project, I think I moved this up so you, now I know which bottle to use. And these were the ship industry, right? The July project. They liked what we did and they asked for more. So we have now a project going with them called Through Life. Where we study the LCA and LCC for the ship industry using modern materials, including bio-based materials. We just been on for a year, but it's running. The team who did the flyback, we started a project called Polyfiber. Polyfiber. Where we try to develop composite material, or exactly making the traditional polyester non-burning. And I have had a workshop here in Umeå this week where we've done full-scale testing of polyester in which we mix nanoclay, nanobentonite. And we know from the test we did this morning that this laminate doesn't burn. Of course, it's not a good solution in the long term because it still uses synthetic material, but it's a step in the right way. And this project will be finished in 1 year. But in parallel, the team that was in the Polytech started another project called Fire Resist. This focused on the resin. This focused on all the different materials within the composite industry. And the driving forces there is ERTS. They are quite famous for their, one of the brands is Airbus, one other is Eurofighter, and of course the shipyards are with and Bombardier. And we learn a lot from the safety regulations from them when we develop these materials. But for me as a person, has the Woody project been the most focused? Although I started that project and I focused a lot on the work there. And as I told you, we focus on wood. And you all know the Christmas tree? And if we go down, we come into the nano level. We can say that you have three main parts. Cellulose, which is cellulose fiber. But the cellulose fiber is not all along the tree. There are small amorphic regions with hemicellulose, a weak part. And those are in bundles that are glued together by lignin. Those are the three important parts of wood. And there are different amounts of them in different kind of wood. For instance, birch wood is like 26–27% hemicellulose. Pine is less than 2% hemicellulose. Cotton is 97% cellulose. It's the cleanest cellulose material you can get. Nutshells, not this nut. Nutshells, are roughly 30% hemicellulose. And it's the hemicellulose that we use for making the resin, that furfuryl alcohol that I talked about earlier. And today, these are mostly taken from bagasse. Bagasse is the scrap you get when you use sugar cane. You take out the sugar and what is left is called bagasse. Mostly from South America, the northern part, Venezuela. A lot is transported to Europe, mainly to Belgium, where they make a resin that is used by the industry that is making cast iron, the foundry industry. They use this to glue the sand. When you make cast iron, you have a sand mold which have the floating iron in it. This is it. But we take that kind of material that is a derivative and make an alcohol of it, which we call furfuryl alcohol, that polymerized at 138, right? Start to remember that. Lignin, it is more or less carbon. So you can make carbon fiber of it, or you can make lignin fibers. And I think you have heard about viscose. Have you heard of the brand Esprit for female clothing? Nearly most of what they're doing are using viscose material. And it's owned by a company from India. And that Indian company owns the Swedish company Domsjö in Örnsköldsvik, who are really focused on making viscose, and perhaps the best in the world. They were here last week visiting me in LG. So there we are back again. It's the same raw material used for different purposes. Okay? And we go deeper in this wood. Because I didn't like the balsa I told you when we made this exhibition things. I wanted to have a better core, not the balsa. And then I thought that this cellulose should be used as a foam. And I have a friend, Professor Gustafsson, down in Jerusalem. We've done some laboratory work and found out that we can make a foam, a pure nanocellulose. Because the cellulose fibers are extremely strong. First of all, they have an extremely good aspect ratio. That means they are very long and very small diameter, long and narrow, even more than me. But they are much shorter than me. The length of a nanocellulose fiber is 1/1000th of the thickness of a hair. Quite short fibers if you compare it that way, but they are very long and very narrow. And if I look upon the Young modulus, E-modul på svenska, the Young modulus of a nanocellulose fiber, it is on the same level as Kevlar, which is originally called aramid fibers, right? Which is roughly 163 rad, and the cellulose is on that level. Right? And these nanocellulose fibers are brought together into wood. They come in different directions, and also with this amorphic region, hemicellulose in between, and it reduces the Young modulus to around 40. And 40 you have in wood, in all kinds of wood. Okay? So therefore, we developed a technique to use these nanocellulose fibers foaming. First of all, we did this nanocellulose and we made it into a foam. We made a suspension with 2.5% nanocellulose fibers in water. And then we took away the water, and the weight will become 25 kilo per cubic meter. That is extremely light. And though it's pure wood, pure cellulose, is very good insulating foam. But when finding about raw materials, here you have the foam. And we can predict, or we can monitor, decide in what direction these nanocellulose fibers should be. So I can make a foam where I put the fibers in a certain direction, all in this direction, or what I want. Because when water turns to ice, it releases energy. Right? You know that is slippery when just around 0 degrees. And this energy is a local boiling. Sometimes you see small voids in ice, right? And when it's just freezing, this energy goes out, you get an energy center, and all the ice crystals is turning into the heat center. And in between comes our nanocellulose fibers. So by using the freezing front, I can decide in what direction I will have the nanocellulose fibers in my foam and the properties of my foam. This knowledge is less than half a year old. That photo is roughly 4 weeks old. What we use is not pure wood. And we don't fight with the industry about newspapers. We take the waste from the paper production. Because when they make paper, you know, they boil it and do a lot of things with it, with the wood. And they want to have the longest part of the fibers to make a good paper. So all the short fibers, they are pressed away into waste. And that waste is processed a bit, so they have invested some energy in it. So it's a perfect raw material for me. So I take that, put my mixer, you know, making the drink, to make it smaller. And when the drink mixer can't make it smaller, I take sonification, ultraljud. And with the sonification, I can make it that small that this turns transparent. It's still a gel inside, but it's completely transparent. And it happens in minutes. And it is that transparent gel that I freeze, take away the ice, and have my foam. And then I can use this light foam of 25 kilo to insulation, or I can infiltrate some kind of polymerization resin into it and get a much stable foam. For instance, I can use the hemicellulose resin called furfuryl alcohol, which I talked about earlier, using as resin with the flax fibers. If I take the same, I get a cellulose foam infused with hemicellulose resin, wood, two different parts of the wood, but pure, no other things there. And this foam doesn't burn. We didn't know that when we did it first time. But some student at our laboratory took one of these parts. Here you have this was a good picture, I've forgotten that one. Here you have the virgin foam, as we call it, the 25 kilos. Here we have infiltrated with this furfuryl alcohol. Here we're taking traditional boat polyester that you make pleasure boats with, and infiltrated and cured it. And then we took these two parts of the Bunsen burner, and this is what happens. Now, Peter, we'll see if it works. That is the hemicellulose part, and this is the one with polyester. And the one with polyester keeps on burning because the polyester is fossil oil-based material, synthetic material burning well, while the hemicellulose-based NCC foam doesn't burn. This is what I call an invention. Of course, there is a patent pending, but it's so recently we've done this, so we haven't got the patent yet. But it's 7 months ago we sent in the patent, so we know that there is no claims against it. Nobody's done it. So Professor Odin Shoseyev and I found this as a good idea. And we see a lot of different applications for this, so we have started a company on it. And we call it Melodia, a melody of ideas. You can find our homepage to www.melodia.eu, of course. So we kind of start a company, and us going to Jerusalem at least twice a month. When we have this beautiful nano-cellulose foam and our melody of ideas, we understood we can do more. One thing was, of course, using other things in life that use the same binding as cellulose. It's called the cellulose binding domain. And some of these materials are called proteins. One rather famous protein is on fleece. This muscle in blue that makes a flea jump like, if I would jump, I could jump up Empire State Building and back 1,000 times without hurting myself. If you come with the size of a cat flea. So we took that protein, which has this cellulose binding domain, because a lot of the body that is fibers is cellulose-based fibers in the body too. But it's not big, much, very small amount. But we could grow it on a tobacco plant and get much more. And then just put it in the centrifuge and get it out that much that we could put it into our nanocellulose. So we put a flexible protein into nanocellulose. Viktig knapp att trycka på över. It's just. There you have the white is the. You don't understand what they're saying because it's Hebrew. It's only I who understands. because it's some water in it. So, and here we have resaline.
Wow.
And it never ends. So we can make your pillow, your mattress, your seat, the backrest of your car, the inside of your car, everything we can make in fully bio-based material. And that is the biggest part we've done so far, is half sugar in size. So we have a bit scaling up to do. But we work it out in the Woody project. And on the 8th of November last year, there was a day of new proposals, new calls for the European Commission. And we sent a proposal there called Firefoam. And we have passed stage 1. Don't know if we managed stage 2. But then we will have funding from the European Commission to develop the non-burning foam, flexible or stiff, with no synthetic materials inside. And yes, the flyback 2 is also on. That's already decided, I just had it. Flyback 2. You see, my time is quite filled with projects. 30 weeks a year, I'm out of Luleå, somewhere around Europe. Usually flying out on Tuesday, back home Thursday, or latest Friday. Always back home on weekends. Can be in Jerusalem, in Newcastle, in Syracuse, or anywhere, riding the project that is on. Developing new things, own patents as a result, because in the European Commission rules for framework programs, you have rules how to handle the IP. And today I've only talked to you about things that I'm allowed to say. Of course, I have much more knowledge, but some is protected by IP that I can't tell you. I think you understand that. So that's where I am now. Having a good time. Just done the polyfire test this week. And next week I'm going to Brussels for a review meeting. It's not most fun thing I can do, but it has to be done. Was that my last picture?
I don't remember.
I think
there's something more.
Yeah, that was my company down there. Thank you. Can I close this one now?
Yeah, I think we have some questions from the audience, so keep it on. Thank you, Tord. It was very interesting, as usual, to hear you. I think one thing I don't think you missed in your presentation was about how to build this trust between partners and what is the important part.
Good. He knows me since roughly 20 years. When he came here to start to study to be a master, I had done my master some 20 years earlier. So. And I think that is also telling you how you make trust. It's always between people. There is no paper that really makes trust that you take a part of yourself and give to somebody else. You can have paper between companies. That is for how you solve problems according to law. And there is regulations about IP and all things. But when you really come to the point to develop something, then you give something of yourself into it. And to do that, you have to have full trust between the persons. You don't get that by coming just together to a meeting. You have to go a level further on. Therefore, it's important when you meet new persons that you also have some socialization. That you go together in the evenings, you do things together, you start to understand and respect that we have families, that we have social lives, but also take part of it. Otherwise, we are not that trustful to each other that really share real good problem solving. So when I started the Woody project, after experience of a few projects before, I started with a meeting that was more on learning each other, because half of the team were new to the others, to make up this relation from the beginning. And it's always a problem when in a company they change position of people and there comes a new person into the group, because even if we are 30, 35 people in a project, we still know each other very well. And today I work with 340 different researchers around Europe. 2 at NTU, 3 at NTU of these 340. But these I trust in. And if I don't trust in the person, I can't give of myself. And I'm that old, I don't spend anything of my valuable time on people I don't trust or like. So if you go into a project and don't do it with your full heart, forget it. That is the reality. The formality, it is well organized by the European Commission when you work in these projects. Because we are now in FP7, the 7 FPs program. And there are good rules, there are alternative rules that you can choose between for every separate project, but there are good recommendations that you have to follow, and it works perfectly. So if there is a conflict of interest, which usually comes when you work during several years with many people, you have rules to follow. But if you have trust in each other, you solve it on a better level than in court. But I've been into court. We had 2 companies who tried to make a patent without telling the other 14 in a project. But we followed then the rules of the commission and solved it. But it was not fun. But shit happens. But those I don't work with anymore. I would never invite them to a project. So it's very much about how you behave towards others, they probably behave towards you. And we have different cultures in different countries, right? And those of you who are not Swedes from the beginning, you perhaps found us Swedes a bit special because we behave very Swedish. We haven't been in war since 1809 in Sweden, outside of course. And that has given us a special way to behave. When I went to my first European Commission meeting, Hypocrat, it was in Geneva, in Northern Italy, in this beautiful Liguria area. I brought my wife with me because it was in June. You know, June here, Liguria in June, mustn't be summer, right? If it's early June. Down there it was 38, 40 degrees warm. So I went to a meeting, 40 people I knew there should be. So I dressed in brown trousers, a jacket looking like this, shirt and a tie. So I thought I was well dressed, looking dressed, went to the meeting, and there came the other 39, all in black suits, except for the ladies who were in black dresses. Everyone was dressed according to what the officer from Brussels expected you to be. You had to show respect for the officer from Brussels, being dressed correctly. Like for a funeral in the same suit. So I was the ugly duck, sitting on the corner, and me, who talks that much, didn't say a word in the whole day. And the meeting ended like 6 o'clock in the evening. I called my wife at the hotel. Shit, I made a mistake, totally. I'm coming to the hotel right now. There's a dinner at 19:30, so we better hurry on and dress up. So I took a taxi to the hotel, and I was sweat, so I needed a shower. And I dressed completely black, white shirt, perfect tie. My wife took on a long dressing gown. She was really beautiful. She is beautiful. And in that one, she was really beautiful. We took a cab and we arrived 5 minutes before the dinner should start in Italy. Right? Then came Donato Zangani with his 2 kids, wife and grandparents, dressed in jeans and Hawaii shirt. Then came the English people, even worse dressed. You know how English people can look with a t-shirt that has been washed 10 times? Well, we dress off. We're here to have a nice evening. Then we dress off and relax. And the officer from Brussels comes in jeans, you know, looking like the English. He was English. So we felt like, not the ugly duck, we felt like, you can guess, not the white swan either. I think I had to do something, because I hadn't said a word during the whole day. So when everybody was at the table, I took a glass of wine and raised myself up and said, now we have to follow the Swedish tradition. I had to do something. And the Swedish tradition say that the one who's coming from most far away is the one who starts talking for the evening. So therefore I'm going to start talking. The first I would say that is that I don't know your habits, I don't know the rules how to behave. And we have shown that. But to me it's no problem. I just take off my jacket, I will take off my tie, I will roll up my sleeves, and now I'm looking just as ugly as you do. But what shall my wife do? These people are since that day best friends. When we go to Newcastle, we always stay in the house by Professor Mark Robinson and his wife Sean. We really became good friends out of this, and at least half of my project I have these English people. So I think being honest in all ways is the best you can. I think it's always that. And you're young, you're making relations with other people right now in life. It's exactly the same as working in a project. It is relations all the time. And if you lie, if you're not honest, you're always the loser, sooner or later. That's from my heart to you. Okay, shall I say something about your projects now?
No, skip.
That's enough. Thank you. Okay.
Any questions from the audience? Or are you flabbergasted?
I have a question, Tord. I know that we have had, we have a history before me coming or working here, but do you have any use for students making thesis works or something like that?
I think we have a lot of students every year in our company. I think we're the company, Lulu, that has no students every year. You know you're always welcome. Yeah. We always have something.
What's the best way for students to approach you?
Call Anton, our CEO. Yeah. And he's done his studies here at the R studies. What do you call that?
Technical design.
Okay. He studied technical design, he's CEO. And he's my wife's son. So he knows what he's all about. And I think we have students more or less every week from somewhere. I think it's very good for our company. Because the dirty guys in the workshop, they see that they can't cooperate with people who use their brain. And that gives them self-confidence. That's not bad. Self-confidence is very important to go through life. Okay.
Okay, any more questions? Or we close the session? Thank you, Tord.
Thank you.